Here is example 2 of finding all the rational roots of this polynomial function of degree 3. Now, I'll go ahead and do some of the work beforehand. So the first step we always want to start out is finding all of the potential rational zeros by using the rational root theorem, RRT, and we know that the zeros have the form of the ratio of all of the positive and negative factors of the constant 36 over the positive and negative factor of the leading coefficient positive 1. So all of the positive and negative factors of 36 are all these, and of course with the leading coefficient positive 1, all of its factors are just plus or minus 1. Putting each number in the numerator over plus or minus 1, we crank out that x can be equal to plus or minus 1, plus or minus 2, and so on all the way up to here. Now the next step is going to be a little more work. We have to do trial and error, take one values of x at a time and plug it into the function to find the remainder and confirm that whether or not the remainder is 0. If it is equal to 0, then we know that the corresponding binomial factor that is equal to 0 from that x value that you selected is a factor of this function. So let's start with x equal positive 1 first. If x equal to positive 1, and of course, x equal to positive 1 is going to give us the corresponding binomial factor of x minus 1 equal to 0. Then by RT, which is the remainder theorem, the remainder f of 1 is going to be equal to, and I'm not going to write out the work because it's easy to do in your head, 1 raised to any exponential power is going to be positive 1. So we got 1 plus 13, which is 14. 14 plus 40, which is 54. 54 plus 36 is going to be 90. But the remainder 90 is not 0, so we know that x minus 1 is not a factor of the function. Now what if x is equal to negative 1, which will give us x plus 1 equal to 0. And you guys know how I got that. Then by RT, remainder theorem, the remainder f of negative 1 is going to be equal to, let's see, we got negative 1 raised to the third plus 13 raised to the negative 1 raised to the second exponential power. 13 times negative 1 raised to the second plus 40 times negative 1 and then plus 36. Negative 1 raised to any odd power is going to be negative 1, so we got negative 1 here. Negative 1 raised to any even exponential power is going to be positive 1. So we got plus 13 right here, minus 40. Positive 40 times negative 1 is negative 40, and then plus 36. Well, let's see. Negative 1 plus 13 is 12. 12 minus 40 is going to be negative 28. Plus 36, but this is going to be equal to positive 8, which is not 0. So the remainder is positive 8, not 0, so x plus 1 is not a factor of f of x. Now let's try the next x value of, let's see, I'm going to select x equal negative 2. So if x equal to negative 2, which will give us x plus 2 equals 0, then by the remainder theorem, RT, the remainder f of negative 2 is going to be negative 2 raised to the third plus 13 times negative 2 raised to the second. Over here, you guys can see it. Plus 40 times negative 2 and then plus 36. Let's see, negative 2 raised to the third is negative 8. Negative 2 raised to the second is 4. 13 times 4 is 52. 40 times negative 2 is negative 80. Plus 36. Negative 8 plus 52 is going to be 44. So that. Negative 80 plus 36 is going to be negative 44. But hey, 44 minus 44 equal to 0. So because the remainder is equal to 0, we get to say that by the factor theorem, ft, the binomial that is equal to 0 from x equal -2 right here, x plus 2, is a factor of f of x. So that means we get to write f of x equal to the product of x plus 2 and this blank factor. But what is this blank factor? Well, using the synthetic division, we set it up by having x equal -2 as a divisor, and we set up the dividend using only the coefficient of the original function, and we list all of the coefficients from left to right in this order. So we got invisible +1, 13, 40, and 36. Always bring out the leading coefficient first, so bring down +1. -2 times 1 is -2. 13 plus -2 is 11. -2 times 11 is -22. 40 plus -22 is 18. -2 times 18 is -36. 36 plus -36 is 0. So this other blank factor right here is going to be 1, and then 11, and then 18. But what goes in the middle? Since we already have one factor of x plus 2 of the original function, the degree of this other factor that we just found here is going to have to be 1 less than the original one. So the original function degree is 3. The degree of this one is going to be 2, so x raised to the second. Positive 11, so we know that's going to be plus. Plus 11. Now we get x squared here, so using the same decreasing order for the exponential power, you know this is going to be 11 times x, and then the constant is just 18. So this right here comes from this quotient. Now we got the factor of x plus 2 multiplying the factor of x squared plus 11x plus 18. Now ask yourself, can we factor out this quadratic expression now? Because this is a quadratic expression, we got 3 ways to go about this now. We can continue going by repeating the whole rational zero procedure here just for this factor. Or 2, we can try to factor it out. Or 3, we can use a quadratic formula for this quadratic expression. In this case, fortunately, it is factorable because x squared has a multiplicative factor of just x and x, so I put it right here. Since the leading coefficient is +1, I get to ask myself, what are 2 numbers that multiply together to give me back +18, but also added together to give me back the second coefficient, +11? Well, that's going to be +9 and +2. So let's see, x times x, x squared. X times 2 is 2x. 9 times x is 9x. 2x plus 9x is 11x. 9 times 2 is 18. So hey, this is the factor form of this. So with the x plus 2, this is the completely factor form of the original function f of x. And the original function f of x equal to 0 as above. So guess what? Using the zero product property, we get to set each of these binomial factor equal to 0. Since x plus 2 is repeating itself twice, I'm just going to write it once. Equals 0. And then x plus 9 equals 0. Solving for x individually, we know this is going to be x equal -2 with the multiplicity of 2. M-U-L-T-I, okay? That stands for multiplicity of 2 because, again, x plus 2 repeating itself twice. For the x plus 9 equals 0, that's going to be x equal -9. So guess what? This is the final answer. These 2 x values are all of the rational roots of this function.